the magnetospheric multiscale mission. NASA EDGE goes behind the scenes with the engineers and scientists preparing these satellites for flight. What kind of tests do they run? Why are these tests important? Find out more as they move one step closer to launch. Next on NASA EDGE.
Hey guys, we're back in studio once again to talk about one of our favorite topics or missions, the Magnetospheric Multiscale Mission.
Or MMS.
Or MMS.
In studio today, we're going to have Troy Cline, who's the Education and Public Outreach Manager, and he has some cool activities he's going to share with us in the show.
I know I'm actually baffled and amazed by these props, and I look forward to the explanation, but I'm also trying to work on stacking right now, which is an important part of MMS.
4 models for 4 identical satellites.
And we're actually going to talk about the testing of these satellites. Each of us actually had an opportunity to sit down with an engineer to talk about exactly what they do to get these satellites ready for flight.
Yeah, I was first up talking with Joanne Baker. She's the Integration and Test Manager for MMS, and she's responsible for all the environmental testing that went on for each of the spacecraft.
Well, my job is to organize all the activities that go into putting the spacecraft together and testing it. So that also includes coordinating all the different teams to work on the spacecraft, put it together, to coordinate the facilities, to make sure that we're ready for various tests and get all the equipment ready and actually get the test run.
Sounds like a pretty complex task. I mean, how challenging is that?
It can be very challenging.
I mean, especially with 4 spacecraft.
Yes, and so it's been quite a juggling act.
Now, what's the status of the 4 spacecraft now?
Well, 3 of them are built, and we are running what we call the environmental tests, which basically puts the spacecraft in different flight-like environments, and then we verify that they are still working. And then the 4th one we're still putting together, and it should be ready in a few months.
Now, when you say environmental tests, is that the same as saying you're putting it through a vibration test to see how the spacecraft would hold up on launch?
Yeah, well, there's several tests that we run. There's as you said, vibration test, which basically what we're doing is we're simulating the launch vehicle. You know, there's a lot of vibration during launch, and so we need to make sure that we can survive that. We also do what we call an EMI test, which is electromagnetic interference test, and we verify that all the components can operate together. And then we also try to figure out, where are they susceptible to noise, so that we have some basic understanding of where our parameters are.
I understand with this particular mission, it's going to be in the magnetosphere of the Earth, and you're going to be taking a lot of sensitive data. So I'm assuming that the instruments are really sensitive for this mission?
Yes, in fact, I think that's probably one of the biggest things about this mission is that we are very highly sensitive. We have to be very careful about magnetics and not contaminating the spacecraft magnetically. So we have to do things like be careful about the tools that we use so that we don't transfer magnetics from the tools to the spacecraft. We have to keep things away from the spacecraft like motors or anything like that would cause the magnetic field to transfer to the spacecraft. Like for the vibration test, there's big motors in the vibration table that create a lot of magnetic fields. And so what we had to do was we had to test the tables and make sure that we were far enough away from the tables when we ran the test so that none of those fields would affect the spacecraft.
Are you building all 4 spacecraft at the same time? Are you building them in parallel or in series?
We kind of did them in a little staggered parallel effort. So we started with the first one, and the first one was almost like our guinea pig. We learned a lot from putting that first one together, so it took a little longer. And then as we built each of the subsequent ones, we got a little smarter and faster at each of the builds.
So by the time you get to this 4th spacecraft, you're just going to whip it out like it's nothing, right?
Yeah, hopefully it'll go a lot smoother, let's put it that way.
Now, at what point do you know that you've done your job?
Really, it's when we see it go up and we see it all work. Once we get through the initial turn-ons and making sure that everything came up okay, that's really the payoff when that happens.
I guess the big question is, how can we do some testing of our own with the models?
Well, we can actually take these, models and go in a car and drive off-road, and we can do it. That would be a good shake test.
Yeah. Shake test, yep, sure.
A record player, microwave oven, maybe?
Absolutely.
It's an important point. I mean, if you think about 4 spacecraft going to the harshness of space, if you don't test for all those conditions, you never know how it's going to react.
And what struck me is that the environments are different at each stage. You have a different environment in the clean room when you're just building and testing the equipment, make sure it's okay. launch in entirely different environments, very rugged, very a lot of vibration, and then space, vast temperature changes. So you've got to test every situation these will encounter along their way.
Right. One thing that Joanne talked about specifically was that the electromagnetic interference that the MMS would encounter in space.
Good point.
And through magnetic reconnection, they need to make sure that the instruments, the suite of instruments on the spacecraft were going to operate. So taking care of that here on the ground was definitely important.
So what you're saying is the people that work in the clean room are definitely not wearing footy pajamas.
Well, you don't want to drag your foot and touch anything.
Yeah, exactly.
But if you did, you want to make sure that the spacecraft is protected. And another part of the testing process is thermal testing. I sat down with Ramel Zaro, who was a thermal engineer, and he told us all about the process. Ramel, what exactly is a thermal engineer?
A thermal engineer is responsible for the thermal control system of a satellite, and that involves the heating and cooling of specific components and instruments within the spacecraft. Similar to a house, you have a heating system and a cooling system, with a furnace and the air conditioning system. Satellite also needs a thermal control system for heating and cooling to withstand the rigors of the space environment, the hot temperatures in front of the sun and the very cold temperatures behind the Earth.
So you basically have to go to the NRL, which is the chamber where MMS is stored for the thermal test, and you have to build the heaters that are used to heat it up, the chamber, or cool it down.
That's right. So we have a fixture that we call the hamster cage. Essentially, it's a giant fixture, maybe 15 foot in diameter. Imagine a hamster cage wheel.
Yeah.
If you turn it to its side, horizontal, that houses one of our MMS spacecraft. And within that cage, we have a bunch of panels that we control temperature to simulate the space environment.
Hypothetically speaking, you get a failure. What is your next action?
So a failure can mean many things. It can be as small as maybe a temperature is off by a couple degrees, right? That's a small failure. It could be as large as a huge box not performing or just being dead. So depending on the type of failure, the mitigation steps can be wide varying. And typically we would test to make sure we understand the problem. So we'll cycle it hot and cold, power it on and off to see if we can diagnose it. And we have a specific failure on our first observatory where we got a thermostat, a thermal control system hardware, that actually failed during a cold cycle on a thruster. So that failure is, I'd say, relatively mild in terms of the range of drasticness, if that's even a word in Google. But we decided to continue testing and to fix that after the thermal vac program.
Have you ever tested a thermal detonator inside the...
Thermal detonator?
Yes.
No, we try not to, like, for example, pyrotechnics to cut deployables. We have done that, yes. So let me take that back. We have tested pyros to make sure deployable mechanisms work. Detonate a small charge to cut a bolt.
Are there any issues that are involved with testing a suite of satellites? Because I'm assuming you're testing one at a time.
Yes, we are.
But if you have to test 4, what kind of time are we talking about here?
Right. I think the main challenge is just the staffing and the time that you need to do multiple satellites. One satellite alone takes about a month of testing, 24/7, around the clock. Holidays, weekends, birthdays, it doesn't matter, you gotta be there. So with 4, it just kind of quadruples the amount of effort that you gotta put in there.
Now, because the satellite will go in orbits in and out of, hot, cold, is that the way you test, go back and forth?
Yeah, so we have some simulations that specifically mimic those temperature swings in space. For example, MMS will have a long period in front of the sun where we're hot. And so we use our radiators to passively cool the system. But then when we get behind the Earth, we have these long eclipses that get really cold, negative 273, absolute zero, deep space. And that's where we use heaters to simulate that cool down and then make sure that we don't freeze. A typical satellite, low Earth orbit, 30-minute eclipses. MMS, we have 4-hour eclipses. So that's one of the major challenges of our design, is to keep from freezing in this long eclipse.
So what happens? I'm thinking of a movie. It's always that movie.
A thermal vac movie, huh?
Well, not a thermal vac movie. It might be a disaster movie. Okay. Someone's in a control room, feet up, test is running.
Right.
and there's a failure. Does a siren go off? Do your numbers change? Do they go from blue to red? What happens?
Exactly like you said, we have sirens actually, alarms. So when we hit, for example, a temperature requirement, it gets exceeded, it gets too hot, it gets too cold. The alarm will beep at you and you get startled, you get up. Other failures like LN2 might be leaking and all of a sudden you get a cloud of gaseous nitrogen like,
oh dude, stop playing Gallagher.
That's when you stop.
Shut the DVD off.
That's right.
You
get up and,
but you don't go in the chamber.
No, the chamber, there's a process for opening that chamber back up, and it's a long process. You gotta repressurize it, that takes time, and then you gotta open it, and then you gotta roll the spacecraft out, so that's a longer process. But definitely there's alarms that'll keep you awake if they get triggered.
Okay. From a thermal engineering standpoint, who would win out? Mr. Freeze or the Human Torch?
Oh, that's a tough one. I mean, I wear both, you know. I'm both superheroes. I keep it cool and I'm hot, you know, so it's like, so it's a tie.
Great interview with Ramel, but Franklin, I'm concerned that you may have created a superhero faux pas in combining Marvel and DC. What, did you do that intentionally?
Well, maybe it wasn't the best comparison to make with regards to the extreme conditions that Ramel tests in, but I guess you got the point.
Yeah, well, I'm sorry, not a good answer. Comic-Con, banned for life.
Troy Cline, what did you think about Ramel and what he had to say?
That was a great interview. I really appreciate it when we can speak with scientists and engineers from such a complex mission, and they can come in and explain it at a level that actually I can grasp, and if I can get it, everybody else can get it, including you, Blair.
Well, that's true. Although Ramel brought up actually created a word, drasticness.
He did.
Which is, you know, I like the freestyle approach he took to the explanation, but I'm going to have to look that one up.
I understood what he meant, so isn't that the point of communication?
Absolutely.
Use your context clues.
Yeah.
Troy, you came and brought some really nice giveaways today. Part of this is actually a bookmark. And if you have a smartphone, and you can use the QR code on the back of the bookmark to find more information about MMS.
We've been using QR codes more and more on many of the products that we come out with because it's fun, actually, when you see a poster with a QR code on it and a satellite, how many people walk by and scan it with their code just so they can play with their QR reader or whatever it is that they have. But what's nice is instead of everything being confined to a piece of paper and the information, which sometimes can change depending on what happens with the mission, a QR code allows it to stay dynamic. So you can just go to a website that we keep updated and to the right page without having to fish through thousands of NASA web pages to find it.
Which is certainly important, especially on a mission like this, because things are happening all the time. Schedule changes, updates. You want to know where the spacecraft is and what's going on, like with the thermal testing and whatnot. So before we talk more about the wonderful props that you have brought, we do want to talk about a very important part of MMS, which is science. And we had the opportunity to talk to Deirdre Wendell, who actually talked about some theoretical aspects of the mission. And so let's take a look at that interview. Deirdre, how will MMS actually help heliophysicists?
It will provide 30 millisecond time measurements of electrons, and this will allow us to, at the same time, measure much smaller spatial scales, because in the previous missions, they relied on the spin of the spacecraft, which is 4 seconds, and many things can change over 4 seconds, so you do miss a lot of information that way. The other advantage that MMS will provide is that it will provide all 3 components of the electric field vector measurements, and that will allow us to measure electric fields parallel to the magnetic field, which is an important characteristic of magnetic reconnection.
I'm going to have to take a lot of that on face value, but it seems to me like essentially what you're saying is we're getting a high-definition view of magnetic reconnection, in part because of the instruments, but also because of multiple spacecraft?
Yes, the multiple spacecraft will allow us to disentangle things that are happening in time from what's changing in space.
Now, how will learning what we learn about magnetic reconnection help us in the future, moving forward in science?
Understanding magnetic reconnection is important to understanding space weather, because space weather relies on coupling between the energy and the mass of the solar wind and the magnetic bubble of the Earth, the magnetosphere. And magnetic reconnection is the primary coupling mechanism between those two regions.
Now, how do we study this reconnection currently before MMS?
They study magnetic reconnection through developing numerical simulations that attempt to reproduce the physics governing reconnection. Another method is to simulate reconnection in a laboratory experiment. There have been certain observations made in space that have contributed to our knowledge of reconnection, but the instrumentation up till now has been much more limited in its ability to provide details about the physics.
So you currently have 3D models of magnetic reconnection?
Well, recently some of the numerical simulations have incorporated the physics of all 3 dimensions rather than just 2 dimensions. And this is primarily because of an increase in computing power that we're able to do that. And this is very important for understanding the realistic physics of reconnection.
Now, did you go 3D because you were bowing to pressure from all the summer blockbusters being presented in 3D, or was there some other compelling reason to drive that?
Well, the motivation was really that people understood that the physics changes when you include the 3rd dimension. The magnetic topology is very different, it's much more complex. And so to advance our knowledge, it was a natural next step.
When MMS flies and we start to get data back from it, you'll be able to apply that data to the 3D models. Will it be able to confirm some of your theories, or will it just make them give you a more accurate picture?
It will probably confirm and disprove certain theories, and as well as providing a more accurate picture, and it may very well present us with some surprises.
That'd be fun.
Yeah.
So there might be a sequel.
Yes, right, a 3D
Nice
sequel.
All right, guys, if I've got to be honest with you, with the beard, I thought I looked far more intelligent.
Well, distinguished.
Yeah, or distinguished, right? Okay, but the interview revealed that I'm not very smart. I tell you, it just blew me away to hear Deirdre talk about the things that are being done scientifically ahead of this launch that will actually confirm theories, that will actually reveal things about magnetic reconnection that we literally at this point do not know.
You know, that really brings in the importance of the whole idea of numerical simulations and mathematics, the importance of mathematics along with the science and the engineering and the technology of a mission like this. Can you imagine what it would be like if something the size of the Grand Canyon, which the magnetic reconnection region, when they touch in space, that little piece where they touch is roughly the size of the Grand Canyon. That's going thousands of miles an hour through space. The spacecraft, all 4 of which are going really fast at the same time. We have to try to bring those 2 events together and capture it, and she said in just milliseconds, where faster than you can blink your eye, is how quickly all the instruments aboard these satellites are going to flash at the same time, or basically snap at the same time. There really are no cameras aboard. But to capture this entire event in 3D, and so that is partially what Deirdre and the people like her are trying to simulate ahead of time through mathematics.
My mind is folding at the drasticness of that illustration.
Drasticness, yes, I like that. Trying to wrap your head around the science and the engineering that have to come together to make that happen.
That's
Grand
right.
Canyon, that thought of that is just mind-blowing.
Well, it is, and one of my jobs is to, as an outreach specialist, is to try to find ways that we can bring people along for that journey. As the scientists and engineers are learning new ways and new information and all of this, we'd like for the public to be able to do the same thing. And about 2 years ago, there was a book that's called Make to Learn. I can share it with you guys. This is basically a hard copy book that was created through an NSF grant in the University of Virginia. And what I noticed was they had 2D and 3D fabricators that they had on the side of one of the shows, and they were showing how students were actually able to explore something like wind turbines and electrical power output out of paper models. So I thought, well, can we do this with the MMS mission? And so I went right up to the people who created this, and I said, hey, we have a new mission going up and it's being built right now. Why not get on board at the ground level as the mission is being developed and help us come up with a storyline and a storybook that does some of the same things that you're doing in this transmedia book? In the end of it all, they created Imaginetic Space, which is a student book talking about a little boy who is on a school bus. He receives a tweet from NASA that says space weather storm in process.
That's real. That's no joke.
And that's no joke. That really happens.
Yes, absolutely.
And there's some intense storms that happen. Well, this kind of concerned him, and he went to his classroom in the story, talks to his teacher, and they end up getting in touch with an engineer from the MMS mission in the story. And that ushers you into the whole process of 2D and 3D fabrication. If people don't have 2D fabricators or 3D fabricators, there are alternate methods that you can use to create the whole process. After Imaginetic Space was created for students, we created a piece of technology, an iBook for the iPad or iPhone, and that will train people how to do all of the activities, and we'll embed it with videos and how-to videos, and we'll also add all the science standards, technology standards, and then we'll create extension activities so that if you'd like to journal what your students are doing with the Student Transmedia book, you can online with about 25 different ed tech tools that they introduce through the book.
By the time MMS launches, would we be able to read some of those journal entries and maybe talk about them?
Yeah, students are actually using the book right now. We have students in a place called Dublin, Texas. I don't know if you've ever been. It's a very underserved community, but they came to us and said we would love to use these materials and test out some 2D fabricators, maybe 3D fabricators, creating different models of the spacecraft, for instance. They're actually even considering trying to create out of a 2D fabricator and paper models a clean room to understand part of the engineering process, and that really blew me away.
I've built a clean room before. That's no easy task.
I saw that episode.
Although I could have used a 2 and 3D printer. I mean, I'm sure that would be the one missing
that might have
ingredient.
changed the outcome of that episode.
Might have changed.
Well, you know, if you had something like an iBook here, you may have been able to help you through that process of putting together your clean room. Then you could have scaled it up to the size that you actually had and may have worked.
Franklin, you're reminding me that I can try again.
Yes, you can.
There's still opportunity out there for me to learn and grow.
Well, there is, and it actually reminds me of yet another school district I have to tell you about in West Virginia. And this is a small school in Paw Paw, West Virginia. They came to us and said, we're really excited about Imaginetic Space and the modeling and all of the engineering and science. We would like to build a life-size model out of plywood, balsa wood. They even found solar panels that they're going to use to create that. And what's really nice is theirs is going to be, one-to-one. It'll be a full-size scale model.
Wow.
So you can imagine the antenna go out 60 meters. That's 180 feet apiece. So I'm not sure how big the gymnasium is going to have to be to contain the...
They'll have to take it out to the football field.
They'll have to, and they'll have a series of activities and workshops and blueprints that they create based on their model that will travel around the state and hopefully...
Travel around the state. Troy, I don't think you realize what you've created in all this through inspiring them. No, you've actually created the 5th MMS satellite. If something goes wrong on the last one, they can just go to Paw Paw, negotiate a little bit and get that fifth
we need to
MMS
tell the students to get their vacuum chamber prepared.
Yeah, exactly. Hey, they got some environmental testing.
Absolutely.
Absolutely. Well, Troy, I tell you what, this is fantastic. It's really encouraging to see, all that you've done, but really all the opportunities people have, not just to learn about it, but to get their hands dirty
And
from
be
a
part of it.
scientific perspective.
That's right.
Thanks so much, Troy. Thanks
You're
for
very
coming
welcome.
by, and we look forward to the next exciting episode following MMS.
You're watching NASA Edge, an inside and outside look at all things MMS.
Good job, Troy.
Thanks.
Do we get to keep these?
You can.
Awesome.
Earrings. Make great earrings.
This is, yeah. Very good.
Dangly ones.